The moment it starts recording, okay. Hello friends, welcome you all to the 22nd session of ARM-based development. Okay, in this class we are going to see something totally different, nothing to do with anything specific to ARM, but it is used in all the processes that we have come across in most of the processes, and it's a very useful format which any engineer working on software or hardware should be aware of. Okay, so whatever system we build is for solving some scientific problem, getting some scientific solution. So we need to know what's the floating point format is all about and how this format is used in any scientific applications for computation. Okay, so this is very interesting topic. You might have come across this in your C programming or any other C++ programming or any programming that you have done in your previous classes or courses. So knowing about floating point representation always helps you to be aware of how a decimal number is represented inside a computer, and when you need to debug something, which will be very helpful if you have a good understanding of this. Okay, so let us now start with that class. Now here I'll touch upon what is the scientific notation all about, okay, and what do we call a normalized number is, okay, and then the IEEE 754 format which is defined to represent a floating point number in a computer. Okay, there are two formats, one is 32-bit wide and another is 64-bit wide. It's called single precision and double precision. We are going to talk more about single precision here, and I will introduce you to double precision, and this is nothing but an extension of single precision to double precision. So maybe we can take it as an assignment to talk about, write up a small paper on double precision numbers. Okay, so get ready, this is very interesting topic. I am very happy to share this with you. Okay, let's start. Now what is a number representation? Okay, so here you know that integers are represented in a computer. You are already aware of 2's complement notation. So what is an integer? So you have a 0 and then some maximum number, maybe -1, -2, you go on till some maximum number, and then +1, 2, 3, whatever you count is an integer number, right? So now when you have a number like 6 and 7, are there anything in between? No, you can represent 6 or 7, right? Nothing in between. So they are all discrete numbers. Okay, and it's a countable number, finite number of items in a finite range. Okay, please remember this finite number of items in a finite range is very important. That is, if I tell you how many integers are there between 5 and 10, 5 and 10 inclusive, then you can say how many are there, you can count it. Okay, right, this many numbers are there, you can always confidently say between 5 and 10 inclusive of 5 and 10 there are how many? 6 numbers are there, there is no doubt about it. But if I ask you how many numbers are there between 2.2 and 2.3, okay, can you tell how many numbers are there? Is it countable? So there is a 2.21, there is 2.211, 2.2113, it can go on and there is no limit to this. Okay, the number of these numbers, okay, between these two are infinite, correct? So there is it's not countable. That's what we are going to talk about in this class. How do we handle these numbers, okay, in a computer? So so far this integers what we have seen is called fixed point numbers, okay. Now real numbers, that's what I talked about, 2.1 to 2.3, okay, you can take anything, right? 2.1, between 2.1 to 2.103, this also there are infinite numbers in between. So these are all real numbers, okay, this is basic mathematics which you are all familiar. So the fractions represented by decimal notation, okay, that's called. Now there are two ways, there are two kinds here if you are aware. 5 by 2 is 2.5. Does it go beyond this division? This doesn't go beyond this. This is called rational numbers. Now what is irrational numbers? A typical very popular example, 22/7 pi can go on infinite, okay. There are some competitions to remember the number of digits after this 3, okay. There are infinite numbers after this 22/7. It's called irrational numbers. So what I mean to say here is infinite numbers exist between two real numbers, okay. Between two real numbers infinite numbers exist. Even if it is the smallest range, you can find infinite numbers exist. This is called floating point numbers. I will tell you why it is called floating point in the shortly. So remember the typical integers that we have seen what being followed in 2's complement notation, okay, is integers which has got infinite numbers in between a finite range, which is called fixed point numbers, and all the real numbers, okay, it could be irrational or irrational, doesn't matter, they are called floating point numbers in the computer world, okay. Let us see. Now a typical example, okay, it's not that this is the largest number I can see. I can find any number I give you, you can always find another number which is bigger than this, okay. Similarly, if I give you a smaller number, if I call it as the smallest number in the real number range, you can always give me a number which is smaller than this. So there is no limit to the real number range, okay. There is no this is 0, 0.0, okay. So there is no limit on how far you can go in the negative range and how far you can go to the positive range. This is positive and negative ranges, but a smaller number is coming towards the 0, okay. Please remember this carefully, okay. There are infinite number of numbers, okay, and then there are 4 limits to that, okay. It's not only 2. The smaller number doesn't go in this way, but they go towards 0, okay. I'll give you an example. Suppose this is 0, I told you. This is on the negative side, this is on the positive side, okay. Let me say this is a positive infinity and this is negative infinity. And what is this which I am calling it as a smaller number? Suppose I say 0.000001, okay. Let me call it as a positive number. It falls here, okay, it comes here just above 0. But does it stop with this? I can always find a smaller number than this by adding one more 0 to it and maybe putting a 1 here. So I can go on. This number of zeros that I can have after this point is infinite. So I can keep on finding a smaller number than what you give me, but I won't reach 0, absolute 0 I won't reach, but still I can find a smaller number I can give you. So this is one kind of a range, okay, which doesn't stop with whatever the smaller number is there. So this is for a positive number. Similarly, there is a positive number which I have shown you here. Then I'll keep on increasing 16, 10 power 16, 10 power 20. Then I can go on. So this also goes on in the positive range. Similarly, there is a mirror image on this side that negative also there is a smaller negative number and a bigger negative number. So there are 4 areas where it can go on for infinite number of times. Okay. So I can never reach an absolute 0 because I can always find the smallest number in the both positive side as well as negative side of 0, and similarly I can have a positive and negative infinite numbers. So that's the kind of a wide range of numbers we have. I showed you only positive here, so I can equivalent thing I can give you a negative of this. So it can expand from 0, okay, on both sides. This is negative and this is positive. It can go on giving me bigger positive number, and this can go on without reaching a 0, a smaller it's a positive number, smaller positive number, and similarly I can go on getting a smaller negative number and a bigger negative number. In that sense, a negative number going towards this end, okay, it's not actually bigger than this side, okay, naturally, okay, it's very logical. But what I am trying to say between these two, okay, this is a smaller negative number, this is a bigger negative number, but this also can keep on going towards 0 but not touching a 0. So absolute 0 is there is no magnitude. So now our problem is, how do we represent this kind of a wide range of number in a computer? So why is there a problem? I'll tell you. Suppose I'll tell you, you have a 32-bit number, 32-bit range, which can vary from all zeros to all 1. Okay. So do you have anything in between? So you are starting from here and ending with this. Okay. If you are given a 32-bit register, okay, assume that you are given a register 32-bit value register, and you are supposed to store a value between 0 to all 1s. How many can you store? There is a finite number of values, right? 2 power 32. Okay. Inclusive of 0 and 1, you can store that many numbers. There is no question of whether is it countable number. Okay, it is countable, but I want to represent a real number range, okay, both positive and negative, given a restriction that I am having only 2 power 32 possible values to represent this whole world of real number into a, see, though 2 power 32 is a bigger number, but it is compared to the range of numbers that you can have in real world is limited. Okay, this is discrete values. Okay, from 00 you can go to next 001, 0010, 0011. So you can go on like this up to all ones. So there is a discrete numbers you can go, but you are using this a restricted world, digital world, to represent a analog, a unrestricted, maybe I can say unrestricted analog world. Okay, see, whatever you see in analog world, what I mean by analog is any signal that you see, you are, all of you may be familiar with A to D conversion, okay, ADC. So when you do this infinite range of analog values get converted into a decimal world, which is a restricted world. Okay, so maybe I can tell you, okay, instead of 32-bit, take for 64-bit. Will you be happy? Still, it is a restriction. Maybe you can go to 80 bits, but all sudden the values that you can represent all can be counted. Okay, 2 power 32, 2 power 64, or 2 power 80. So you are trying to use one of them to represent the real world scenario. Okay. Now, how does the floating point representation help you in doing so? Okay, we are done with the initial introduction. So all of you are familiar with the scientific notation from your school days. So scientific notation is a way of writing numbers that are too big or too small, okay, to conveniently written in a decimal form. Okay, whereas in a normalized scientific notation, a fraction with a non-zero leftmost digit is said to be normalized. Okay, without giving an example, this looks little confusing. No issues. Let me give you an example. What are these? This is called scientific notation. Why? See, if I need to represent this whole thing, okay, without having this convention of 10 power minus 10, I would need a miles of length of paper, okay, right. So I am compressing it, but are we losing out something in the scientific notation? Of course yes, because you are not representing the decimal numbers. What are the, it could be varying from 1 to 0 to 9, right, the decimal values. So it could be 10.1, 2, 3, 4, 5, 8, 9, no, it could be anything. So this uh, finer details are lost, okay, to give a compressed form of representation. So when you write it, that many decimal points are lost, okay. And okay, let me erase this. So what is this notation? Is this different from this number? Certainly not, because when I move this the decimal point that I have to left, the 10 becomes 1.0 into 10 power minus 9, correct. This value and this value are same. Now I like to move this decimal point to lowest. Suppose I write like this, then I write it this way. So it is this notation. Now I can still go on moving this point further and then write it this way. So all these values are actually one and the same. Only thing is, where do I fit the decimal point decides the exponential part of the 10, the decimal number system. Similarly, this is a towards representing a smaller number, and if I am trying to represent a bigger number, I have both the rotations are same. But is there any limit on how many forms I have in this notation? Okay, there is no limit. So there are many unnormalized forms. This is called unnormalized. Okay, so I can have n number of notations, both in terms of positive, smaller value or a bigger value, and it could be for positive or a negative value. Okay, normally we don't tend to write plus if it is already a positive number, but we uniquely represent a negative number with a negative sign. Okay, so if we put a negative, then you get a other range of the number, the other side of the 0. Okay, so there are infinite representations using this notation, which is called scientific notation. Now what is normalized? Let us read again this. A fraction, okay, a fractional number, but it is not an integer number, it is a fraction with a non-zero leftmost digit, okay, to the to the decimal point, okay. So it's a non-zero leftmost digit, okay. What this, see, any notation I have a non-zero leftmost digit, okay, okay. But here after the decimal point, I have a decimal non-zero decimal digit, but I don't have a digit. See, it says leftmost digit. I have non-zero leftmost digits. Okay, let me remove this. See, here after the decimal point, I have a non-zero leftmost. If I say leftmost means it should be only one and digit. Here there are two digits are there. Okay, after this decimal point. Here it's not non-zero. Okay, here two digits are there. Though it is non-zero, is two digits are there. This is non-zero. It is a zero actually. It's not a non-zero value. So none of them fall under this normalized notation form. Okay, let me show you what is the normalized scientific notation. See here, this is only one digit after the decimal point is a leftmost, and there is only one, and it is a non-zero value. Is this scientific notation? Yes, it is a 5, which is only one digit, which is non-zero after the leftmost point of the digit. So effectively, these two are a normalized scientific notation. Can I have, for representing the same value, can I have one more normalized scientific notation? I can't. What about this? No, I can't have one more of a normalized scientific notation. There is only one representation, which is this for this particular value. Okay, so that is what is called normalized form. It is unique for a given value. Please remember, it is not that only one is there. There are so many infinite number of scientific notations are there, but it is unique for a particular value. So what is the advantage we get? We are getting a unique representation using the normalized notation. So in a digital world, we need to have a unique numbers, and there is no confusion between two. The same value is represented in two forms. We are leading into a confusion, right? So in a real world also, real number world also, in the digital domain, we are trying to represent with a unique normalized form. So we are going to select this notation for our floating point representation. Okay, got it? Okay. So now you are clear about what is normalized and what is unnormalized. So there is one digit, a non-zero digit after the decimal point. So this decimal point is moved. Okay. Suppose I give you a value. Okay, and then ask you to represent it in a normalized form. What will you do? You move this decimal point to 1.023. Okay, there is no point in representing the 0 because beyond this I have not given you anything. So my no, I am not representing this number beyond this. Okay, so do I have to do anything here? Of course you have to do, because you moved it 3 digits, 3 decimal points here. So I will multiply it by 1000. So this is my normalized notation. So I can have only one normalized notation for this number, correct? So that is what I am driving at. Okay, so floating point numbers. Let me tell you, similar to the world of decimal world, I am giving you I am giving the base of this is a binary. So I'll give you a normalized notation of this number. I'm sorry, this is not what I have shown you. So suppose I give you this. What is the value in the decimal notation? Very simple. So anything to do with the decimal point here, left to this is given 2 power 0, 2 power 1, 2 power 2. It goes on like this. Suppose if I had given a number like that, and then after the decimal point, I will add. If I find a 1, I will write 2 power 1 by 2 power 1, 1 by 2 power 2 plus 1 by 2 power 3. If I have a 0, I will multiply it with 0. If I have 1, I multiply it with 1. So this is how I represent it in the decimal in the binary world. So given a number of like this, I say okay, 1 into 2 power 0 is effectively 1, and then I add 1 into 1 by 2 power 1 by 2 power 1, which is 1 into 2 power minus 1, 0 into 2 power minus 2, and 1 into 2 power minus 3. So how does it convert into a decimal value? This is 1. This 1 by 2 is 0.5. This of course 0. This is 1 by 2 power 8. This is 1 by 2 power 8 converts into 0.125. Add up all of them. Then this is the representation in the binary world. Is this a normalized notation? Of course, because after this binary point, I have a non-zero number. In our binary world, non-zero is only, it could be only 1, right? In a decimal world, it could be from 1 to 9, right? A non-zero value in a scientific normalized notation. In a decimal notation, where in a binary notation, I can only represent a non-zero value, means it has to be a 1. So now I have a binary representation of a normalized scientific form, and I have given you how to convert it into a equivalent decimal form. Good. Okay. let us go to a generic format for this. Okay, so this is the scientific notation I said. Okay, now suppose if I give you a number like this, can you find out what is the equivalent decimal number? So 1.0 is nothing but 2 power 0 1 into 2 power minus 1, which is 1 by 2, which is 0.5. So 1 into 0.5 is 0.5. So if I tell you, okay, I can give you some few binary places for you to give this value x, okay, and then I give you some finite binary, decimal binary points to represent these y's. Then you can represent in a in a binary world a real number, correct? Suppose I will give you an example. Suppose if I tell you you have 4 digits to represent your value. This I am giving you 4 digits for this x, okay, and then into 2 power plus or minus, okay, this also plus or minus. I tell you 4 digits for representing 1 some number. So suppose if I convert this, because I am giving you, because after the point you will say that this is 2 power minus 1, this is 2 power minus 3. So you will add up, it is equivalent to this number, right, 625. But what do I multiply it with? Suppose I chose a plus with, this is a unsigned number suppose, then what is the equivalent of this? 8 plus 2, 10. So 2 power 10. So 1.625, okay, into 2 power 10. This is the equivalent binary decimal value represented by this number. Provided I have given you, you can represent some binary values in 4 locations. So effectively what I am trying to say is, suppose you are given a space to represent this sign number, okay, plus or minus, and then you are given 4 digit, okay, locations to represent this number, this 1016 here, where is my, okay, and then I have given you 4 more digits to represent 2 power something. So that also happens to be 101. Now I need to give you another space for a plus or minus here, okay. Assume that I have given you, I missed out one more sign bit for this exponent portion. So plus or minus, in this case it is positive, so it will be 0, and in this case also I have given you a positive number suppose, okay, it is not a negative number, then I will write as 0 here. Then effectively how many bits you have taken? Here 1 bit. So 4 plus 4 8 plus 2 10 bits if I give you, then you can represent some real number which goes up to 1 point some value into 2 power 10. Okay, it's a big number, quite big number, right? So now it is a general format, and but I am going to give you a format which is going to be conventional, universally unique, universally agreed upon, so that 2 different processors designed by 2 different people from 2 different countries will represent a binary floating point number in a given notation, okay. So it can't be arbitrarily, I cannot say 4 here and 4 here and the sign bit here, somewhere in some notation I will say sign bit is here. So if suppose everybody implements a floating point or a real number representation in a computer, using different formats, it will be difficult for 2 processors from 2 different countries or companies to work together. They won't understand each other, okay. So there should be some universal notation for everybody to follow. That is what the IEEE 754 has tried to do it, okay. Before we come to that, let us see some advantages of having the scientific notation. Simplifies exchange of data. That's what I just now said, okay. You can compute something in one computer and then give it to the other one, they will understand it better, or not even better, they will understand it correctly. Simplifies arithmetic algorithms. So because of the standardized notation, the implementation of some addition, multiplication, all that can be uniform, okay. So it simplifies the algorithm. Increases accuracy of the numbers that can be stored in a word. since unnecessary leading zeros are replaced. Okay. So one more advantage I didn't point out. See, suppose if I have a number like this, okay, sorry, 100 point, okay, 000, there are, or suppose there are 1.2. So if I tell you this binary number is not here, it's not here to the end, end, and you have a leading zeros. Okay, one example is, in this case, you take an example here. You have to store all these zeros here. Okay, but if I bring it to the non-zero and then multiply by 2, okay, I don't have to store all these non-zero numbers in the binary representation. So I can try to bring it and then I can move that to the exponent part, but some accuracy may be lost. Okay, I am not saying that it is a panacea for every problem, but you are able to store some numbers with a reduced number of bits. Okay, when you want to leading zeros you want to avoid. Okay, and then bring it to a compressed notation. So you are trying to say, okay, I will have one non-zero value followed by some numbers. Okay, if there are there. So this is the scientific notation. Okay. Now let us go into a floating point general format representation. Okay. Okay. Now I am representing this. Call it as a B, B, and E. These are all binary bits. Okay. Now suppose if I have a generic notation like this. Okay. And what is missed out here maybe is maybe I can mention it as a plus or minus here. Okay, exponent also can be positive or negative. Okay, maybe should have been there, not an issue, because exponent is a, I mentioned it here. So for simplicity for your clarity I am writing it here. See here, plus or minus could be represented by one bit. Okay, and if suppose that bit is set, that is sign bit. Okay, if it is 0, this what will happen, minus 1 whole power 0 becomes 1, anything to the power 0 is 1, so it becomes a positive number. Okay, but suppose s is 1, yeah, the sign bit is 1, this will become minus 1 to the power 1, which is minus 1, so this becomes a negative number. Fine. And then I am saying this is normalized form, that means it's a non-zero to the leftmost number is a non-zero value, so happens to be a 1, so it is always fixed to be 1 point something. Now tell me something 1 point some number is there. Okay, I told you this whole thing is added by finding 1 by 2 plus 1 by 2 power 2 plus 1 by 2 power 3, so on. Suppose if I have up to n digits. Okay, happens to be, okay, if suppose this is 1 to n I have, okay, n numbers, then I will have plus log 2 power n. You agree? So I keep on adding some smaller and smaller number as I go towards this. Forget about this one for a moment. If I need to calculate the value that I get by converting these decimal numbers into a real number, I need to do what? If I encounter at 1, I will put that many, which if it is a second bit position, I will say 2 power 2. If I get a 0, if I have a 0, I will ignore that number. Okay, like this I will convert. What do I get? Will I get any time more than 1? Okay, some value I am getting after this conversion, val. Will it any time be more than 1? It can't be. because it's all a smaller number. Even if I add all the smaller number, it will never tend to, it may tend to become 1. Okay, it will tend towards 1 limit, no, this val tending to 1. Okay, but it will never become 1. It will be a fractional part. Okay, that is very important to keep in mind. So this portion, what I add is a conversion of these values. This is 2 power 1 plus 1 by 2 power 2, so on, is a fractional part. Why am I adding 1? Because this is 1 anyway. Okay, this is actually converted into by 2 power 0. So I am adding 1 plus this fractional part to find out the decimal equivalent of this. Fine, this I have done. Now if I suppose convert these bits into some value, and if I say it is a 2's complement form, if I tell you that it is represented in 2's complement form, that's why I am not giving a plus minus specifically. So 2's complement form means suppose 4-bit value, then this will become a sign bit number. So I will find some negative number, right? Some negative. Okay, convert this into a, what do? I inverse this 1 0 1, which happens to be 5, so minus 5, correct? If I convert this into a negative number, it will become minus 5. So whatever number I am representing, I can convert it into some positive value or negative value. So what I will do, I will multiply that to the power e. So minus 5 if I got, I will take 2 into 2 power minus 5. So effectively from the binary notation I will be able to compute some real value from here. You agree or not? So this is a number representation. Okay, so let me read up whatever I have given here. So S is a sign bit, F is a fractional part which is called as significant. So this number of bits that I give you represents the precision, how precise my numbers are. See, if I give you more digits to represent here, I am increasing the precision of the value that you can represent. Suppose if I give you 20 bits, you can represent 2 power 20. 1 by 2 power 20 is much a smaller number, so you can even represent a maybe weight of an atom, or maybe a smaller number, maybe distance between an electron and an orbit. Okay, between two nucleus and an electron orbit in an atom. So I can represent a much finer details if I give you more numbers, more digits to represent the fractional part of the number. So it improves my precision. Okay. What if I give you more number of bits to represent this portion of the thing? I am increasing the range of numbers that you can represent, both in terms of positive and negative, correct? Plus or minus. So if I give you more number of bits here, you can represent more and more bigger values either towards positive side or towards the negative side. So exponent portion gives you a wide range. Number of bits that you give for a significant part of the representation gives you more precision to the number. Okay, so that's a balance between these two you have to get, because in a computer the number of bits you have is limited. Okay, 32 bit or 64 bit I told you, so it is limited. So in a given number 32 bit, you have to represent some fractional part and some some exponent part, correct? Few bits for this and few bits for this. Okay, and then why am I giving you this? This is a sign bit for maybe this portion, the whole number. Okay, and exponent part I am giving you 2's complement. See, you should not get confused between this plus minus and this plus minus. Okay, this plus minus tells you whether this number falls on this side of the fence or this side of the fence. This plus minus, okay, positive negative. This sign bit gives you whether this number is to the left side of the 0.0. Okay, I should not write 0, maybe 0.0. Whether it is here negative or positive. Now, what is this plus minus gives? This tells you whether this number is, once you are decided, okay, I tell you that this is negative, you are coming to this range, but I told you that it could be on this end of the spectrum or a smaller negative number. So if it is negative, the exponent portion is negative, you are the number what you are representing is falling on this side of the fence. But if this is positive, it is falling on this side of the negative number. That means it's a huge, a large negative number or a very small negative number. Similarly, that is true on the positive side. Suppose this is a positive, then this plus minus tells you whether it falls on this side or this side. So there are four ranges, and there are two positive negative for that. You should be clear about. I am sorry if I have, this is positive negative, this is positive negative, you have 0.0. Okay, so let me call this positive as A, then where does it come? This number is here. Fine. Within A, this positive, if I call B, okay, this number is here, A and B. Now in A, if it is negative, if I call this as the C, then it is here. Why? If I give you a smaller E value, that the 2 power minus something I am giving you, so it is going to take you to a smaller number, because this is anyway it is 1 point some small number multiplied by 2 power some smaller number. Okay, so it is going to take you towards a positive smaller value. So where does the D belong to? Suppose if it is negative, it will come here, that is smaller negative number. So you will be able to find out where does a number belong to based on this is positive or this is negative. So there are four combinations possible, and the four numbers are this or this portion, it may lie here or it may lie here. Four values. Okay, so this should be clear to you. I won't be explaining this. Now one more point I would like to highlight here. In a floating point representation, this leading one bit, see this value I told you is always happens to be 1. In that case, do we have to say store this number in the 32-bit value we have? It's a waste, right? I told you that S bit is there, 1 bit is stored, and then there is a floating, fractional part is represented by some bits number, and then some exponent part is there. So do I have to save this number? I don't have to, because it is always implicit. So 754 has followed a convention that this 1 bit is not represented inside the floating point. Okay, that means we are not reserving a bit position for this. Please remember, in a inside a computer, decimal world, every bit consumes power, consumes space, consumes energy. So we don't want to waste anything inside a computer. So if we can default assume that it is going to be 1, why not do away with that? Okay, so only these bit patterns are saved in this location, so that you get get one more bit position for either increasing this or increasing this. Okay, very good. So general format, I am just explaining you. Fractional part is between 0 and 1. So this portion is, it is always between 0 and 1, and exponent portion is computed to the power of 2, and as mentioned earlier, the leading value of 1 is not stored. Okay, it is a implicit number stored in the floating point representation. Okay, I am just elaborating on what I explained in the last slide. So let us do an example. Okay, suppose if I represent it like this, I have given you a value, okay, like this, and this 2 can be represented by 0 0 1 0 based on number of bits reserved. So what do I get? I convert it into equivalent. You can you can freeze it and look through this. It's not very complex. These values are computed based on this bit pattern, and then into 2 power minus 2 is nothing but 1 by 2, and then this by 4, and this is the decimal value. So finally, any bit pattern given in this form can be converted into a real number like this. That's what I am giving you. an example. Okay, fine. Okay, let us now come to, so this is the real number 0.0. Okay, now I am showing you some underflow, overflow. Okay, because I told you that we have a limitation of 32 bit. Now you know that sign bit is given. I have not still told you how many bits are occupied by fractional part and exponent part. No issues. Well, maybe this may lie here or it may lie here. Okay, please don't even lock onto this. I am just showing a generic notation. I have not yet shown you IEEE 754 notation yet, but I gave you an example that whatever comes in fractional part will be here. Okay, into 2 power some exponent part will be here, right? This much I explained you, and this one is not stored as a part of this, and this plus or minus is given here. Now, okay, this dot, let me make it clear. Now I am bored with the red. Let me change the color to avoid monotony. Now you see here, I told you there are ranges, right? Okay, this is more or less closer to this. So 4 ranges are there. Okay. Now, because of the restriction on number of bits reserved for F, number of bits reserved for E, I can't represent the whole range of real number. Of course, it's not possible. So there is a limit. Now, how do I reach those limits, and how do I know that I have reached a limit? Okay. So using both this fractional part and exponential part, when I am representing a number, plus or minus, I get into one of these ranges. So the fractional part takes me as close as possible towards a 0, but doesn't take me into 0, right? So even if I say that this is the lowest number, I can give you a smaller number than this. So it will never reach 0. So there is a limit. Okay, this some portion is not reachable at all for a given number of bits reserved for a fractional part. Similarly, after some exponential portion, I can't reach beyond some value here. So there is a limit on both positive and negative side based on what I have here, plus or minus. So based on this exponent plus or minus, I have a limit on this number also. So there are, similar to what I told you, that 4 ranges, there are 4 overflows and underflows are possible. What I see here is a negative overflow. What I see here on this side of the fence is a positive overflow, and there are 2 underflows also. Positive underflow, which I can't reach a absolute 0 because there is a smaller number which I cannot reach. I can't go more precise than this because of the limit on the number of bits I reserved for fractional portion. So similarly, there is a negative underflow. Okay, so this you should understand fully. So my limit on expressible numbers are lying here. Okay, maybe I can show you in a different color if you are bored with the. Okay, my limit on a positive and a representable negative numbers are here. I can't represent these numbers which are falling in these ranges. Anything beyond this, okay, where is my cursor? Here, okay. Anything beyond this, and anything within this, and anything within this. Got it? This you should always have in mind to have a better understanding of floating point. So overflow means it's a positive exponent which is too large, okay, to fit in. So there is a limit because of my 32 bit or whatever 64 bit or 80 bit, whatever I call. And similarly, underflow is, this is an event where a non-zero fraction has become too small that it cannot be represented. It's a non-zero. I know that it is a non-zero, but I can't go and represent it because my fractional part has run out of it. So I have put all zeros, and then I can, if you give me more digits for the fractional part, I will give you, I can represent a 1 here. So I am not giving a fractional part, so it is gone. So because of that, it's a non-zero fraction. So this situation occurs when the negative exponent is too large to fit in the exponent field. So it is a negative exponent which is too large to fit into this, and similarly I can't represent the fractional portion also, because see the negative exponents gives you a smaller number along with the 1 point something, because this is 1 point, it is a 1 plus something. So effectively this negative number only is going to take me to a lower value which is closer to 0. So that also has reached a limit. So underflow and overflow are happening because of the limits in the representation. Now let me come to floating point representation, which is the standardized notation of IEEE 7654, sorry 754. So he is the person who has invented this notation. All we should really feel happy to be for his invention, because we are able to solve all the scientific problems using computers because of this notation, and he is the person behind the invention of Intel 8087. If you have heard about 8086, it had a co-processor called 8087, okay, which was a floating point processor, okay. So this was invented and he was the designer of that particular processor, okay. So IEEE took his notation and standardized it across the industries. So everybody who develops the floating point coprocessor need to comply to this, but they gave some freedom to for the designer to play around with that. Okay, let us go to single precision. Why do I call single precision? This is the lowest possible 32-bit notation which was standardized by IEEE. Okay, so far I was showing you some floating point, that exponent portion, and this was in a wrong locations. That was intentional. I don't want you to lock on to that, but you should know when you are working on IEEE 754 notation where the exponent portion comes and where the floating point, the fractional portion comes. There is a reason behind this. Okay, I will explain you. The exponent portion is here immediately after the sign bit, and then the fractional portion. Now how many bits are reserved for that? 8 bits are reserved for this, and 23 bits are reserved for this, and 1 bit for sign bit. Now it's adds up to 32 bit. Okay. Now you may wonder where is the sign bit for exponent? It is all internally given here. Okay, in the exponent notation. Okay, so now onwards, let us not play around with the location of exponent and fraction. Even I will show you, to scale. Okay, this is exponent portion, this is a fractional portion, this is a sign bit. Okay, this is 8 bit, of course this is 1 bit, and remaining 23 bits are here. Let me write everything here together. So this is the standard notation. Okay, let us not play around with this. Now let me tell you one important point. The exponent is defined like this. Okay, I will explain you in the next slide. This is called bias notation. Okay, so it is varying from -126 to +127. If you recall a 2's complement notation, okay, let me explain here. 8-bit number. Okay, I told you exponent is 8-bit number, so it will vary from 0 0 0 to all 1 1 1. Fine. If you have a limit on how far it can go, right? 8-bit number. Now, if you know 2's complement, of course, you should, all of you must be familiar. This representation corresponds to this, and this corresponds to, I'm sorry, here it is 0. Okay, let me route it here. Here, correct? This of course 0, right? 0 to +127. Okay, and 1 all 0 0 0. Okay, between these two. Now you have a question whether this corresponds to minus 0 or minus 128. Let me convert this. This is a MSB is set to 1, which is 2's complement is a negative number. How do you compute the magnitude of this number? You invert all of them. Okay, I invert all of them and add 1 to it. What do I get? Minus 1. So if you were alert, you would have caught me wrong. So this represents minus 128 and this represents minus 0, minus 1. So this is the range. Okay, 0 to, okay, let me draw, okay, let me write it in a different color. Okay, just for that I am writing it for some purpose. Okay, 0, this is plus 127, which one? This representation, and then this is minus 128 and this is minus 1. Okay, let me erase these guys. Now you see here this number is going from 00 to 111. The values in 2's complement are, oh sorry, I erased this also, are going like this. If this is not very useful or very helpful in comparing the representations of a number which is changing from 0 to some bigger number. Okay. For one reason is 0 to 127 comes and then the negative number, the most negative comes very close to immediately after this most positive, and then the negative numbers go in a reverse direction. They keep increasing towards this. If I draw a 0, minus 128 and 127, so 0 to 127 goes like this, and then they come from minus 127 to this. So it's not going, from the big pattern wise, it is not increasing or decreasing in one format. That is the problem with the 2's complement. But though it is very helpful for arithmetic and then storing integer negative numbers, they are not straight away compared against like a unsigned number. Unsigned number is no issues. It keeps increasing from here. Unsigned number will go from 2 to 0 to 255. Okay, so they increase in one way, whereas here they are in a different direction. They are increasing. The 2's complement notation. So the floating point, they wanted to do away with this. Okay, they want to map it differently. I will show you. Okay. Oh sorry, I don't want to erase this. Anyway, no problem. 127. Okay. So instead of doing one more, okay, let me tell you. Now one more thing, what they did was they took away two numbers from this for some special purpose. Okay, that means 0 and all ones are taken away in the exponent. For a moment, assume it is not used for a typical exponent notation. So what are you having at 0001, and then what is the next one just prior to this 1110, which is happens to be a FE. Okay, so this is 1. Okay, so these numbers are only used for the exponent notation. This 0 and 1, all ones are considered to be a special representation. Now you are having only a 1 and here, and this is if we are following 2's complement, it is a difficult form. So what was done is, okay, they mapped these numbers, the floating point representation, into this notation. Okay, that means any number, okay, you subtract it by 127. Suppose if I tell you whatever you have, whatever the range of values you have, you subtract it by 127 to get some number. Now I told you 1 is the range you have, and then an unsigned notation you have 254. Okay, 0 and 255 are knocked off. 0 and 255 are knocked off. You have the remaining numbers. Let me change color again. So you do a minus 127 and then see what do we get. You get minus 126. Fine. Then I have another unsigned number 254. If I do minus 127 here also, what do I get? Plus 127. Now suppose I represent any number in the exponent notation by adding this bias. Suppose very simple, if I want to write 1, okay, I want to write 2 power 1, exponent is 1, okay, I want to write plus 1, what do? I won't write it as 0001, where I have 8 bit here, I won't write as 0001, I don't write it that way, I do minus 127, okay, and then write it as whatever I get, I will get minus 126, I write minus 126 here, which happens to be f of e, this notation, this number, okay. So I write it in this form, which is 2's complement, suppose, okay. So effectively what am I trying to do? My most negative number comes as it's represented. Now if I go back in a different way, okay, that suppose this is the number I wanted to represent, right? If suppose so 1 I want to represent, I represent it as 127, okay, which is minus 1 okay, minus 126. 1 second, I think I got confused. Okay, let me rephrase what I said. Okay, I told you 0 and 255 are not used for representing the number. Now 1 to 254 are used for representing the exponent portion of the number. Okay, let me erase some portion of this here, okay, to give you clarity on this. Okay, so when I have a negative number which happens to be, I want to write 2 power minus 126, okay, what do? I add a bias, okay. So minus 126 is added with 127. Let me tell you, this is the bias I am adding. What do I get? I get 1, okay, this is the number. So effectively this is nothing but minus 126. Okay, if I write a 1 there in the exponential portion, it actually represents minus 126. So how do I get back? See, while storing the number, see, remember this is the number I want to my 2 power minus 126. While storing it, I add a bias of 127 and then store it as 1. So while interpreting the number, I need to do the same thing, reverse of that, right? So I will do subtract of minus 127 from the number whatever I see in the exponent. I get, what do I get? Minus 126. So the hardware, okay, by interpreting the value stored in exponent is subtracting the minus 126, sorry, minus 1, no, subtracting 127 to get the actual value that 1 represents. Now what does the 254 represent? Same logic, okay. Suppose I want to know what does 254 represent, what I should do? Same thing I did what I did for 1. I subtract 127 from there. What do I get? I get another 127. So this is actually positive 127. So this will correspond to positive 127. 2 power 127 I will represent it this way, and minus 126 I represented this way. Got it? Now what do why am I doing this? What do we gain by this? See here, if suppose if it is considered as just a binary number, a representation of 1 is happens to be a smaller number compared to anything below this, correct? 254 or anything above this is this is smaller, isn't it? So that is true in the range of the numbers also. So minus 126 is given a smaller representation in a unsigned notation. Okay, you consider it as a bit pattern. In unsigned notation, minus 126 is given a smaller notation, and then compared to positive 127. So how does it help me? It helps in comparison. Suppose if I give you a floating point number, knock off the sign bit, I let me see the exponent number and floating point number, the fractional portion. This portion, if it is a smaller number as 1, it's a minus 126, right? 2 power minus 126. So it's a smaller number compared to a bigger number. Similarly, if any bit pattern I see here, if it happens to have a number, suppose 0, 0, 0, 1, and then 0, 0, 1, 0, 0, 1. Suppose this is the end of the number. Anything having a bit pattern in the higher portion happens to be a bigger number compared to anything only having a 1 here, because this is 2 power 1 by 2 power something, and this is 1 by 2 power 23, 23 or whatever, a higher number. So what I am saying is, together with the exponent value and the fractional portion, I can directly compare a integer comparison I can perform and find out whether this number is a smaller or a bigger number. So comparison becomes easier. I am sorry for this whole lot of numbers written here, but just concentrate on these ranges are taken based on the bit pattern, and this 1 and 254, this is all 1 except the lower LSB 0 happens to be a bigger number compared to this number. So this representation is easier for comparison of two floating point numbers. Okay, that was the intent for doing. Okay, so sorry for taking more time here. Let us go forward. Now, what are the ranges of values represented here? So one more thing I need to explain here. If you recall, this has an implicit notation 2 point this fractional part into 2 power exponent part. Okay. Now let us concentrate on the smaller number and the bigger number that you can represent here. I am telling you that 2 power minus 126 is the smallest number. Why? Minus 126 is the exponent portion. So this is a plus or minus 1 point all 0 suppose, and then followed by 2 power. The exponential portion is the smallest number that you can represent is 2 power minus 126. Now this is the smallest number represented, okay, because 1 into this is this, so just a 2 power 126 is smallest number. But how do I say this is the biggest number that I can represent? So what does this 2 minus 2 into the power minus 123 represent? For this I need to take a little bit of detour. Okay, instead of 23 numbers, assume that there are only this many notations. Okay, only 3 bits are given to you, fractional portion. Okay, suppose I represent all ones. Okay, what does it correspond to? It corresponds to 2 power 0 plus 2 power minus 1 plus 2 power minus 2 plus 2 power minus 3. You agree? What does it correspond to? 1 plus 0.5 plus 0.25 Okay. Okay. So for simplicity, let me remove this also. Just 1.11. Okay. Now what does it correspond to? That's all. This corresponds to 1.75. You agree? 1 plus 0.5 plus 0.25 is 1.75. Can I represent this number in another notation? Suppose if I say 2 minus 2 power minus 2, because I am given 2 bits instead of 3 bits. Okay, so for simplicity I removed it. Okay, now this corresponds to what? 2 minus 1 by 2 square, that is 2 minus 0.1 by 4 is 0.25, which is nothing but 1.75. So any number represented as 1.11 can be represented by 2 minus 2 power 2 if it happens to be 2 bits, right? You agree? I proved it. Okay. Now I am given a 23 bit patterns here. 23 bit. Now if it happens to have all ones, which will correspond to some 1 point all 1. How many ones? 23 ones, right? Which will be equivalent to 2 minus 2 power minus 23. You agree? Because 1.11 corresponded to this, then it will correspond to this value. You agree? Now 1 point, all these are all 1. Okay, because I am trying to represent the biggest number possible. Now I need to put all ones here in the fractional portion, and then my maximum the number that I can have an exponent as 127. So this will correspond to the maximum positive number that I can represent. Sign bit happens to be 1, then this will be a maximum positive number. Okay, both are maximum positive ranges. Negative will be negative of this. That's all. So effectively, I have told you that this is the range. I hope this example clarifies that. Okay, and the equivalent value of the decimal equivalent of this. Okay, I represented in 2 power something, right? If I convert into decimal form, this is 1.17 into 10 power minus 32. Quite a small number, right? In a positive world, and this is 3.4 into 10 power 32. If I put a sign bit as 1, I will get a equivalent negative numbers also, right? So this is the kind of a range I am getting with the best 32 bit values. That is the beauty. But please don't think that I have all the infinite range between these two. It's not. That range is again limited by 2 power 32 notations, and out of it some formats are left out. So you have a less number of discrete notations, discrete numbers possible to be represented between these ranges, both in positive and negative world. There is not infinite number of ranges available because you are restricted to the bit patterns, which can range from 2 power 32, maximum 0 to 2 power 32 bit patterns you can have. So only a limited way, in a sense, you can represent them, but you have a wider range. You can represent numbers which are falling between these two ranges. Okay, that's the beauty of floating point representation. Okay, so what is, I am just explaining a bias notation which I explained in the last slide. So effectively range is from 0 to FF, 0 and FF are reserved. Okay, and we have a remaining 0 to FE. You add up bias, okay, of 1 to 7. Any value in exponent you minus 127, you get the actual exponent value. Okay, that's how you should get the actual exponent value. You get the pattern here and then subtract it from 127, you get the actual value, which I explained you earlier. Bias of 127 helps in performing an integer comparison of floating point representation. I told you that you can easily compare to floating point numbers. So 0. Now one more limitation on this notation. Okay, because you are assuming this 1.0 into 2 power something exponent, you can never represent a 0 with this notation. So you need to have a special representation. That is where this reserving this number helps you. If reserved happens to be, if exponent happens to be 0, or okay, it represents a 0 value. That's the beauty of this representation. Okay, because if I give you any value between these two ranges, it will always assume that 1.0 something, right? So you can never represent a 0 when you have a 1 in this place. So this notation, the normalized notation, doesn't help you in representing a 0.0, because this always starts with 1.0. So any value which is starting from 1 with multiplied with the 2 power something, it could be a fractional portion. Okay, so you cannot represent anything just as a 0. So for that, the exponent portion 0 is reserved. Okay, I will explain you that. Let us go into this. Now this is easy to understand. This is the range of negative number or positive numbers in integer world, which you are all familiar. And here I am telling you that the limits on the format, see, plus or minus 1 point, all ones correspond to one of the negative or positive infinite values. Okay, actually maximum what you can represent, if all ones are there, 2 minus 2 power 223, which I told you earlier, and then 2 into 2 power 127. This is the number. Okay, here somewhere here. And then if it happens to be all zeros, then you are having a number here. Okay, because 1 point something into 2 power minus 126. So it will bring down that value to something which is little bit more here, but it doesn't come to the 0. Okay, it will be 1 point something, so it will be 2 power minus 126. So that is the maximum negative value, or sorry, that is the maximum, the lower number you can represent, positive and negative number, 2 power minus 126. Okay, it is not just 1. Okay, please remember, it is not added. This is not here, it's not added to this number, it is multiplied. So it is 1 into 2 power minus 126. So you will get a sub 0, sorry, less than 1. Okay, but it is something 0 0 0 or something. Okay, which can be up to 2 power minus 2126, but it will never reach the absolute 0. So that is what is called a negative underflow, which I explained in the previous. Okay, I think this is clear to you. Let us go a little faster. So this representation is called normalized notation. Okay, anything above 0 and less than maximum. That means what? 0 1 exponent value being 0 and fe. Okay, is a normalized form, and any bit pattern can be there. This is a normalized form. For a moment, ignore this. A 0 can be represented with all zeros here and all zeros here. Now you have an option of sign bit being 1 or 0. So if it happens to be a 0, okay, it is a positive 0, and so you can represent a positive 0 and negative 0 here. Similarly, if all ones are given here, because I told you that 0 0 and ff are reserved. Now if ff is given as exponent, it represents a infinite number, infinity. Okay, you are not able to represent anything beyond this, so you have put f here and 0 here. So you can represent both positive infinity and negative infinity here. Now you are left with some bit pattern which you can use it here. Okay, with all ff here and with all ones here, which are used for denormalized form. I will explain that in the subsequent session in the class, in the slide. So let us defer it for a moment. Okay. Now I am going into the details of summarizing it now. So exponent is varying from 1 to fe, and it is calculated by 2 to the power whatever value is given minus 127, and then a binary point followed by 1 something, which is called the fractional portion. The whole thing 1 plus 0 is called mantissa. Okay, that's the convention, mantissa, and this is called fraction. Okay, this is called fraction, and the whole thing is called mantissa. Okay, complete it. And then mantissa can vary from there 1 to 2. Okay, the mantissa value what is represented here can vary from 1 to 2. Okay, it can never touch 2 because 1.9999 it can become, but it can never become 2. So this whole thing gives you that value followed by the multiplication 2 power something. Okay, so this is the representation. So this will help you. You know, maybe you can freeze it and read through this. And the multiple is 2 power minus maximum. So the fractional portion increments by 2 power minus 1 to minus 2 3 because one bit here actually gives you the last bit gives you minus, sorry, if I am writing it below it will be 2 power 23. So this one bit gives you this. If you increment this by 1 it becomes 1 0 which is right this much. So you are incrementing by every time 1 by 2 power 23. That means it is equivalent to 2 power minus 23. So the fractional part gives a multiple of 2 power minus 23. I hope it is clear to you. And then minimum positive normalized number is, I told you, 2 power minus 126 to this, which we have already seen. This is all given for a completeness sake. Now positive and negative zeros, I told you this is 0 and this is one positive, and if all 0 and this is also all 0, that means it's a 0 value. So you have a 2 zeros. So positive and negative zeros can be represented in a floating point value. And then I am explaining a normalized number. See, I told you you can never reach a 0.0, right? So you reach a 2 power minus 126 if I recall correctly. Okay, and then 2 power minus 126. This is negative and this is positive. Now negative, infinity is here, negative infinity here, positive infinity here. But I want to represent something even lower than this. Okay, is it possible? It is not possible currently with the normalized form because I am starting with 1.0. That's a normalized notation. Suppose if I can do away with this 1.0, then I have a freedom to go into a much more lower value than this. That is what is used here. That means if the exponent portion is all 0, okay, and then this is a non-zero bit pattern is given, then it is no longer a normalized form. It is called a denormalized form, and the value is computed using this equation, plus or minus based on the sign bit minus 1 to the power s into 2 power minus 126. This is assumed. You have reached a maximum of the smaller number. Okay, though you are having a 0 here, this range is assumed. Okay, 2 power minus 126 into the fractional portion by assuming 0 point the fractional portion. Okay, so it is no longer 1 point something, 0 point fractional portion. That means you are still bringing down the value that you can represent in the lower region, these two lower regions. So basically what you do, 2 power minus 126 into how far you can go lower into 2 power minus 23. You agree? The least LSB is 1 is the least you can represent, all zeros followed by 1, and you are assuming that it is a 0 point something. Then you can go up to 2 power minus 23, which is nothing but minus 149. You add up these two, you get this. So this is the minimum positive denormalized number. And what is the minimum negative denormalized number? Minus this, correct? Is the same on both sides, right? Window. I'll go back to the previous one. Sorry to go back here. See here, these two are plus and minus of the range, which is minus 126 earlier. Now I have brought it lower than this, up to 2 power minus 149, and then this is brought into this up to 2 power plus 149. Oh sorry, this is minus only, Only thing is this is plus, sorry, okay, this is minus and plus. Let me write it here. Minus 2 power minus 149 plus 2 power 149. So it is brought into some more. Still it cannot reach 0, but it is better than previous. Where in a no, denormalized form. Okay, this is the form. So in the floating point, that flexibility is there. You can represent with this value all 0. Even if you represent as all 0, you are always assuming it as 2 power minus 1. Who is assuming? The floating point processor who is implementing this would assume. Okay, and then it will take out the fractional portion and then give you the value. Okay, so I hope this denormalized form is easy to understand to you guys. And then plus for infinity and positive infinity, all ones followed by zeros are plus and negative infinities. Okay, so this is what is explained here. Now the interesting portion is a not a number. Suppose you have all ones followed by a non-zero pattern, it is called a not a number. Let me go into some more details here. Why it is required? The exponent is all 1. The value is either an infinity or a not a number. So when this is now, if it is all zeros with all ones, it is called a infinity. But if it is a non-zero pattern, it is called a not a number. So DSP architecture. So the not a number representation is actually given specific, the independent implementation. Any floating point processor representation can free to use this pattern to convey something internally within the processor, okay, on some floating point arithmetic happening. So I will explain you why it is given. So in the VFP, that is the vector floating point processor, which we will be seeing in the next class, they are given the value sign bit followed by, here they are giving the bit 22 is given for the sign bit can take any value and the remaining fraction bits can take any value except all zeros. So there are 2 power minus 22 minus 1. That means the sign bit can take any value and the remaining fraction bits can take any value except all zeros. So they are calling this bit 22 as a sign bit, and the remaining bit pattern, that is 22 patterns you have, can be anything other than 0, because it has to be 1 minimum. That means one non-zero will be here and this can be a 0 or 1. That means they are taken care of all ones here and a non-zero value here to represent a NAND, and then that is given as a possible signaling here. Okay, and then this is called signaling NAND. Okay, not a number. This is called a not a number, and if it happens to be 0 or 1 followed by a non-zero pattern, bit pattern, that's called a signaling NAND. And if suppose sign bit is a 1 and this all, okay, 1 second, this bit pattern has to be 0. Okay, it cannot be a 0 or 1. It has to be a 0, and then a non-zero bit pattern is called a signaling NAND. And then quiet NAND is, this is 1 followed by any value from 0 to all 1. That is called a quiet NAND. Now, what are the reasons for these two? I will just give you in the next slide. Quiet NAND is, this is the propagate unchanged through most floating point operations. So suppose when you are performing some floating point operation, there is a error has happened or you are not able to represent the number, then you can put a quiet NAND. Then that value representation pattern, you can put a pattern here, that quiet pattern, that is the bit 22 is, okay, 1 and then followed by a 0 to 1, all ones. Okay, that is a quiet NAND. If it happens to be a 0 and then any non-zero pattern is called a signaling NAND. So basically these two are given to represent some internal representations of floating point results which are understandable by the floating point processor. Okay, and then basically by the application also. So this is to generate, if you are not able to generate any sensible result, you can put a value which is called not a number to represent that intermediate values. Okay, and then further any calculations depend on that, we will continue to be using this NAND number. The quiet nans can only be generated in this way if associated with the invalid operation. Okay, if you are generating an exception, if the exception is untrapped, you use a quiet nan. If it is trapped, then trap handler is called. See, floating point I will be explaining in the later session. So I thought I will talk about nan here. If you don't follow this, maybe you may have to read some literature to understand this. Because of the time limit, I'm little going faster here. So if it is trap is there, then you don't have to have a quiet nan representation. Otherwise, if you don't also use any trap, then you can have a quiet nan number into the floating point method. Okay. Another typical use of quiet nan is to represent missing values. Okay. And then missing value in the sense, suppose you are initializing a value and then you can initialize it with a quiet nan, and then if a particular floating point number is not initialized and then you are using it for a represent computation, then this quiet nan will indicate to the exception handler that that number was not initialized. Okay, the results of any calculation can that depend on the missing value are also quiet nan. So you can propagate this value. Suppose the error has happened in the floating point in between the computation. The quiet nan representation is used to internally propagate that value into the computation. Signaling is done. Nan is done for invalid operation exception whenever any floating point operation receives a signaling. So this signaling nan is used for creating an exception. Okay, for creating an exception, the ARM processor, suppose floating point is creating an exception, the ARM will be having a unsigned instruction exception, which will take it to the exception handler, which is specific to the floating point operation, and then it will carry on with the value what is to be done. So it is used for debugging and uninitialized variables. So preloaded memories can be initialized with signaling nan. Please understand that all the signaling nan and quiet nan are very implementation specific, and they can be used according to the implementation. So IEEE standard does not specify how these two types are used and how many values are reserved for them. Okay. So it says that one or more of the operands to an operation with a floating point result in a NAND. Okay. If any NAND operand is signaling NAND, an invalid operation can generate an exception. If it is untrapped, it should be changed to quiet NAND. That's all. Quiet NAND actually basically needs that it is quiet. That means it will not generate a exception. It will immediately, it will quietly follow that exception. It will absorb the exception and then keep a quiet NAND in the representation. Whereas signaling NAND has to generate an exception. That's all you should understand. The result must be, if a NAND operands are quiet NAND, the result also should be a quiet NAND. So example of NAND operation, intermediate form, operations with a NAND at least, if it has the one of the operand, with a NAND as at least one operand, and then if there is a 0 by 0 or infinity by infinity happens in your computation, then you can generate a NAND operation, NAND representation. Okay, and or you are trying to do a plus infinity and minus infinity addition, or this addition, or you are powers of you are doing a 0 to the power 0 or 1 to the power infinity. They are all not representable. So you can use the NAND representation for doing that. So these are the different usages that you can have in the NAND representation. And then real operations with the complex results. Suppose you are trying to find a square root of negative number. This happens to be a imaginary number. If suppose you have only no complex number, then you have to use a NAND for that. Logarithm of negative is also not defined. Similarly, sine inverse cannot be out of this range, minus 1 to plus 1. So any number which represent which can't be represented in a typical floating point number, you can use the NAND representation to handle those situations. NANDs may also be explicitly assigned to variables, okay, to show that they are uninitialized. That's all. Now we are getting into a 64-bit representation, which I am not going to go into the detail. This you can take it as an assignment. Okay. Here I will only tell you what is the representation. This is a 64-bit representation. See, bit 20 to 30 are reserved for exponent portion. 11 bits are reserved. In a floating point, 8 bits were reserved. Now we increase the exponent range, and then earlier it was 23 for fraction. Now it is 52. Okay, sign bit is of course you don't need more than 1 bit. So what do we gain by this? We are getting a range of numbers which are unimaginable. 10 to the power 308. If you recall the signal precision, you had a 10 power 38, I think, was the range. Here you are getting 10 power 308. It's a huge number, and the bias is now 1023. Okay, it is not minus 123 as was shown in the single precision. It is 1023. Of course, there is because of 11-bit exponent quotient, which you should write it as an assignment for your understanding of double precision representation. And extended precision is called 80-bit. So with this we are coming to an end of the floating point representation. I hope it was useful to you. And if you don't follow any of them, please read and this and then read through the documentation or any of the manuals or books to have a better understanding. And if you have a good understanding of the floating point, you will be in a position to debug, understand, and write and design your own coprocessor for a floating point arithmetic or any other DSP or any scientific applications, any processor needed for it. Okay. Thank you for your time and attention, and let us see in the next class. Thank you very much. Have a nice day. Bye bye.